Hello, everyone. Welcome to a lecture on digital logic design. The major topic that we are going to discuss is combinational logic with MSI and LSI. The subtopic for the today's lecture is programmable logic arrays. These are combination circuits which are used to implement different Boolean functions. Here is a simplified general block diagram of programmable logic array. I will explain the building blocks of programmable logic array. We have n inputs in this PLA and m outputs. So basically, it's a combination circuit with n inputs and m outputs. These n inputs for every input there is an complemented form of that input and a normal form of that input. For example, if there is a Boolean variable a, then a prime is also produced and just a is also produced. So the next block is k products. We have a set of k AND gates in a PLA. Just like Rome, there were, if n were the inputs, then 2 raised to power n were the AND gates in the decoder. But here we have k AND gates or k product terms. The value of this k is normally less than or equal to 2 raised to power n. If it is equal, then it's similar to Rome. But the main objective of programmable logic array is that this k is much less than 2 raised to power n, and that is the beauty of programmable logic array. Otherwise, it would be similar to Rome. Okay, so we have k product terms, and there is an AND gate for each product term. So if we have k product terms in a PLA, then we have k AND gates in this group. To each AND gate here, the input variable is connected in the normal form as well as in the complemented form. This is the complemented form and this is the normal form. Then the link is either broken or kept connected depending on if the normal form or complemented form is connected to that particular AND gate or should be connected to that particular AND gate. Then we have another set of gates, OR gates. Each OR gate represent or logically implement a sum term. So if we have m sum terms, then there are m OR gates. Every OR gate logically implement a sum term. We have k cross m links between the two group of gates. Every AND gate here is connected to every OR gate through a fuse. So this fuse would allow us whether to connect an AND gate, the output of an AND gate, with an OR gate or not. So this will allow us, this will give us the flexibility that is the major feature of programmable logic array. Next, we have m outputs. If there are m Boolean functions, then we have m outputs. But this output, every output is taken from the output of of OR gate, just like we did in the ROM. But the difference between PLA and ROM in this place is that the output that we take from every OR gate can be complemented if required. So there is an inverter and there is a bypass link through the fuse. If a function is to be implemented in the complemented form, then this fuse can be either kept or broken. For example, if the product terms are calculated by taking group of zeros in the k-map simplification, then obviously the original function was not implemented and its complement it was considered. So that complement should be removed by taking another complement by passing the output through the inverter. And to do that, this fuse should be broken so that the final output is taken from the inverter, which would complement the complemented function. So that would mean we get the normal function at the end. I will of course show you an example in the coming slides. So this concept will be much clearer. Okay, so just to summarize this block diagram, we have n inputs, and every input is complemented. A complemented version as well as normal version is given as input to every AND gate. Here we have k AND gates, and every AND gate is to implement a product term in the Boolean functions. We have m sum terms, we have m outputs, then we have m sum terms, and every sum term is implemented with OR gate, and every AND gate in this set is connected with every OR gate here through a fuse. So we have k cross m lengths, and similarly we have m outputs, and every output is taken from the OR gate and then passed through an inverter as well as a fuse. So depending on which the function is implemented in complemented form or normal form, this fuse is used to do that correction. Okay, so let me show you an example where we implement Boolean functions using PLA, and we decide and then design a specific PLA of a particular organization where the number of n, the value of n, k, and m are specified here. So this is a simple example to implement two Boolean functions using PLA. These two Boolean functions are given in the sum of minterms form. f1 with variables a, b, c is equal to sum of minterms 3, 5, 6, 7. So this f1 is represented with sum of minterms, and f2 with variable a, b, and c is equal to sum of minterms 0, 2, 4, and 7. So these two functions are represented in sum of minterm form. If they are not in the sum of minterms form, then there are a number of methods to convert them to sum of minterms form. If the Boolean functions are directly given in the truth table, then it is quite easy to implement them in the sum of minterms form. Just write the minterms where the output of the function is 1. Just combine those minterms, and that will be the sum of minterms representation like this. And similarly for f2. So if a truth table, if the two functions are given in the truth table, then it is quite easy to write them in the sum of minterms form. If they are not, then they can be converted by mathematical manipulation using Boolean algebra to convert from other forms to sum of minterms form or sum of product. Sum of minterms form. If Boolean functions are given in the sum of minterms form, then the first step is to represent them in the sum of product form. If they are in the sum of product form, then one must be sure that they are in the simplified form. And if they are not in the simplified form, then they should be simplified using K-map or any other method to represent them in the sum of product form, in the simplified form. So these two functions, if they are given in the sum of minterms form or in the truth table form or in the standard form, they can be simplified using K-map method. So whatever the form you are comfortable with, just convert the Boolean functions to that form and then simplify them using K-map and represent them in the simplified sum of product form. So in this example, we have the Boolean functions in the sum of minterms form. So just we directly simplify them using 3 variable K-maps. Because the two functions are 3 variable Boolean functions, we simplify them using 3 variable K-map. So let's begin with Boolean function f1. This is the map per Boolean function f1. The empty spaces where nothing has been written, like empty square, the empty square here, they represent zeros. So the main terms where the output is 1, main term 3, 5, 6, 7, they are written, those the corresponding square are marked with 1. For example, main term 0 is not there, 1, 2 is not there, 3 is there, 4 is not there, 5 is there, 6 is there, and 7 is there. So 3, 5, and 6, 7, these four main terms are part of the Boolean function, so the corresponding square are marked with 1. And the rest of square, which represents 0, are left empty. So you can write 0 otherwise. Okay, that's fine. Okay, so we have Boolean a K-map for the three variable Boolean function f1. Now we have to group the squares where we have marked 1. So we can make groups of squares with 1. For example, here these two squares can be combined into a single square group. Another group is to combine these two squares. We can combine these two squares into a group. We cannot combine these three squares in a group where the group would have 3 squares, because that is not allowed. Because of the number of groups, the number of squares in a group should be in the form of 2 raised to the power n. So you cannot write 3 in the 2 raised to the power n. So this is the number of squares 3 in a group is not allowed. Similarly, you cannot combine 5 squares in a group. You cannot combine 6 squares in a group. You cannot combine 7 squares in a group. But you can combine 8 squares in a group, and 4 and 16 and 32 and so on. Okay, so the next group is to this one should be added to a group. So the better way is to combine it with this square so that we can make a group of 2 squares instead of 1 square. So we have another group which combines 2 squares. So we have included all squares with 1 in a group, and there is no square with 1 that is not included in any group. So we have 3 groups, and each group consists of 2 squares. So now we can create product term for each group. For example, the product term for this group is A, C, for this B, C, for this A, B. So the Boolean function f1 would be like this. f1 is equal to AC plus AB plus BC. So we have 3 groups and we have 3 product terms for the Boolean function f1. This is represented in the sum of product form. Similarly, Boolean function f2. So this is the map for Boolean function f2. Every main term that is part of the Boolean function, the corresponding square is marked with 1. The rest of squares are left empty, but they represent the squares with 0. So you can just write zeros if you like. Okay, so we are interested in the squares with 1, so we just show them, and we can make group of squares as we did with Boolean function f1. So we have a group consisting of these 2 squares. We have a group consisting of this square with this one because they are neighbors. And we have a single square group which consists of this square. So let's begin with grouping. This is the first group of 2 squares and the Boolean function f2. And this is the second group, and this is the third group. So the Boolean function f2 would be b prime c prime plus a prime c prime plus abc. How? Look, the product term for this group is b prime c prime, because b prime and c prime both covers this group. So the term for this group is b prime because b prime is here and c prime is also here. So b prime c prime is the product term for this group. Next, this group, this square and this square forms a group of 2 squares. So a prime and c prime. C prime covers this whole group. So a prime and c prime is the product term for this second group, a prime c prime. Next, we have the final single square group, which which is covered by A, B, and C. So A, B, C is the product term for this group. So we have finally define the Boolean function f2 or created Boolean function f2, which is directly represented in the sum of product form. So if we the functions are given in the sum of minterms form, they can directly be written over to corresponding three variable k-maps, and after simplification we would get functions which would be in the sum of product form, and the forms would be simplified forms. So we got two Boolean functions f1 and f2. We considered the squares where the value of the function was 1 at that particular square, and we obviously through this approach we got the functions f1 and f2 in the normal form. If we group the squares with zeros, which are represented here as empty, if we combine them, then we would get the Boolean functions in the complemented form. So this approach can also be taken, and we will analyze which one is better in this particular example. So let me show you how can we create Boolean functions in the complemented form. So this is the map for f1 where the empty squares are now mapped or marked with zeros. So these are the empty squares, now they are zeros, and the empty square here now represent the squares with 1. So they are not just they are not written, but if you like you can write them with 1. That's okay. Okay, so we have Boolean function f1, and the squares with zeros are the minterms which are not part of Boolean function f1. So obviously they are part of the Boolean function f1 prime. So if we group Boolean squares with zeros, then we would get Boolean function f1 prime instead of f1. We got f1 in the normal form, we would get f1 in the complemented form here. So let's begin with grouping the squares with zeros. So we would have, this is a group of 2 squares, this is a group of 2 squares, and this square would combine with this one would make a group of 2 squares. Okay, so this is the first group of 2 squares, and f1 prime, the first product term of f1 prime is b prime and c prime. So this is the product term for the first group of squares, and obviously this is f1 prime because we are making group of zeros, so that's why the function that we would get would be f1 prime. Okay, next we can combine this square with this one, and we can create a group of 2 squares, and the product term for this square is a prime b prime, because a prime covers these 2 squares and b prime also covers these 2 squares. So a prime b prime is the product term for this group. Then we can combine this square with this one to make a group of 2 squares. Remember that we could also create a group of single square instead of combining with it. That would also be correct, but that the function that it would result would not be in the simplified form. So to get a Boolean function in its simplified form, then we must create group with as many as squares in the group, and the condition is that every group of squares must have at least one square which is not in a group before, which is not part of any other group. So for example, this group has this square new, in this group we have this square new, which is not already in a group, and in this square is new, this is not part of any other group, and this square is part of 3 groups, so that is okay, it can be part of as many as other groups. Okay, so we have 3 groups of squares, and we have calculated Boolean function f1 and f1 prime, and these are the product terms. Now we do the same for Boolean function f2, and here is the map of Boolean function f2 where the minterms which are not part of the Boolean function f2, the corresponding squares are marked with 0. The minterms which are part of Boolean function f2 are left empty because they represent 1, and the other minterms which are not part of F2 are marked with zeros. So obviously by making group up squares with 0, we would get F2 prime, just like we did with F1 prime. Okay, so by looking into this map, we can create group, and the first group would be like this. This is one of the groups. These two squares would make a group of 2 squares. Similarly, we can combine these 2 squares to make a group of 2 squares, and this square cannot be combined with any other square, so this would be a single square group. So now let's begin with grouping. Here is the first group, and the product term for this group is B prime. Here is the B prime and C. So B prime and C covers all the squares of this group. So the first product term of F2 is B prime C for this group. Next, we have a group of 2 squares here, and the product term for this group is A prime, because A prime covers all the squares of this group, and C. So A prime C is the product term for this group. And finally, we have a single square group, and the product term for this group is A, B, and C prime. So A, B, C prime is the product term for this group. So we have included all squares with 0 in a group, and we have created product terms for all the groups. So this is the Boolean function F2 prime in the sum of product form. So for these two Boolean functions F1 and F2, we have represented them and their complemented form in the sum of product form. So now we can analyze whether we should go with considering F1 and the functions in the normal form for the calculating set of product terms, or in the complemented form, or we can also follow a hybrid approach where one function is in the normal form and the other function is in the product form. And our goal here is to get a set of product terms, and the number of product terms in the set should be the minimum. Either of the approach, which would give us least number of or the minimum number of sub product terms in the set of product terms, we would follow that approach, and we will take that combination of functions. So let's begin with that, and we get the set of product terms. If we consider the complemented form of these functions, which are highlighted here, these functions in the complemented form are given here. F1 is equal to the product terms here and whole complemented. Similarly, F2 is equal to here. So these are the product terms of each function. If we get the set of product terms from these two functions, which are taken from the complemented form, then we would get this set. This is the set of product terms. We have 1, 2, 3, 4, and 5 product terms. 5 product terms would be part of this set. B prime and C prime is common in both, so we take it just once. So we have 6 terms here in F1 and F2, but we have in the product term set we have 5 product terms because one product term is common in both, so we take it once. This is the set of product terms when we consider F1 and F2 prime. Now, if we consider F1 and F2 in the normal form as highlighted in the slide, so we get F1 here AC plus AB plus BC, and F2 is equal to B prime C prime plus F prime C prime plus ABC. So these are the two functions represented in the sum of product form. Now the set of product terms would be AB, AC, A prime SC prime, BC, B prime C prime, and ABC. No product term is common in both functions, so we get 6 product terms in this set. In the previous scenario, we got 5 product terms. In this scenario, we got 6 product terms, 5 and 6. So at least we now know that considering the complemented form is better than considering the normal form, because in the normal form we get 6 product terms, and considering the complemented form we get 5 product terms. So we at least know that considering the complemented form is better than considering the normal form. But we can do better than this by following or adopting a hybrid approach like this. If we combine F2 in the normal form and F1 in the complemented form, then we get this. F1 is in the complemented form, so we get the product terms here, and F2 in the normal form, then we get the product terms here. When we remove the redundant product terms, then we get the set of product terms here. B prime, C prime. B prime, C prime is part of both functions. We just write it once. F prime, C prime. F prime, C prime is also part of both functions. So we write it just once. F prime, B prime, and ABC. So we got a set of 4 product terms. This is the best solution here. In the first scenario, we got 6 product terms. In the second, we got 5. And in the third one, we got 4. So this combination is the best one. So you would follow this one. We would get F2 in the normal form, and we would get F1 in the complemented form. So we got the set of product terms, which is the minimum, 4. Okay, so next we create program table for these product terms. Here is the program table for these product terms. We create 3 columns. One column is product term, and one column is for the inputs, and one column is for the outputs. In the product term column, on the left side of this column, we just write the product terms that we have decided. These are the product terms. So we just write them: B prime, C prime here, A prime, C prime here, A prime, B prime, and ABC. We just wrote these product terms to the left of the product term column. And in the product term column, we just write or number them. We have 4 product terms, so we just number them 1, 2, 3, and 4. This is just for simplification. You could also skip this numbering and you could just write these product terms in the product term column. But writing 1, 2, 3, 4 is simple than writing B prime and C prime in the implementation. So this is just for convenience to number them here. So in the product term column, you just number these product terms. We have 4 product terms. We number them 1, 2, 3, and 4. And just to remember which is the product term number 1 is B prime and C prime. So we write them to the left of the product term column. And the inputs column, there are 3 sub columns because we have 3 inputs A, B, and C. So we create 3 sub columns A, B, and C because we have 3 variables. If the Boolean functions would be 4 variable Boolean function, then we would create 4 sub columns, for example A, B, C, and D, and so on and so forth. Similarly, for the output, we have 2 Boolean functions, we have 2 outputs, and they have already been named as F1 and F2. We just create 2 sub columns. Now we have to fill the middle entries, and in the inputs there are 3 possible values: 0, 1, or dash. In front of each product term and below these variables, write 1, 0, or dash. If the variable is in the complemented form in the product term, then write 0. If it is in the normal form, write 1. And if it doesn't exist there, write dash. I repeat, in the inputs column, beneath these variables, write 0, 1, or dash. Write 0 if the variable is in the complemented form in that product term. Write 1 if it is in the normal form. Write dash if it doesn't exist there. So A doesn't exist there, so we have to write dash here. B is in the complemented form 0, C is in the complemented form 0. Similarly for the output, if the product term is part of that function, write 1. If the product term is not part of that function, write dash. For example, B prime C prime is part of F1, B prime C prime is part of F1, so we write 1. B prime C prime is part of F2, so we write 1. If it is not there, then we write dash. So let me fill in this row here. A is not there in the product term B prime C prime. B is complemented, C is complement, B prime C prime is part of F1, B prime C prime is part of F2, or just simply this product term is part of F1, part of F2. So product term 1 is part of F1 and also part of F2. So we write 1 in on those columns. Now we fill the same row for product term 2. Now A is in the complemented form, so it should be 0. B is not there, it should be dash. C is in the complemented form, it should be 0. Product term 2, A prime C prime. A prime C prime is part of F1 here, so we write 1. A prime C prime is part of F2, so we write 1 here. So let me complete this row. B is not in the product term 2. Similarly, for the product term 3, A is in the complemented form 0, B is in the complemented form 0, C is not there, it should be dash. A prime B prime is part of F1, it should be 1. A prime B prime is not an F2, so it should be dash here. So let me complete this row. So F2 is dash here. C is not in this product term, so it's a dash. B is complemented, A is complemented. Similarly for the product term 4, A is there, B is there, C is there, and they are in the normal form. So 1, 1, 1. And similarly, ABC is not part of F1, so it should be dash. ABC is part of F2, so it should be 1. Like this. F1 dash and F2 it is 1. And for the inputs ABC it is 1 for each of them. So we have completed the 4 rows for the 4 product terms. Finally, for the outputs, either we write T or C below F1 and F2. The value in this row can either be true if the function is in the normal form, or complemented if the function is represented in the complemented form. Now we know that F1 is in the complemented form. Look, we had considered F1 prime, and then we just to get F1 we had to complement the right part of the function. So here we have the complement, which complements all the terms of the function F1, so it is in the complemented form. So under F1 in this row we write C because it was considered, the complemented form of F1 was considered. And for F2 we write T because F2 is written in the normal form, so we just write T, that means true. So let me fill this row. So we have C for the complemented and T for the normal. Okay, so we got the implementation table or the program table for the PLA. Now we would use this program table to program the corresponding PLA created for these 2 Boolean functions. So now let me create a PLA for these 2 Boolean functions, and then we would program it by looking into this program table to program the PLA, the desired PLA. Okay, so this is the program table, and now what would be the organization of the required PLA to implement these Boolean functions? We have inputs, which is represented with n, 3, because we have both of the Boolean functions are 3 variable Boolean functions. So we have the value of n, which are the inputs, that is 3. Outputs are 2, which is represented with m. We have 2 Boolean functions, so we have 2 outputs, and we have 4 product terms, which is the value of k, and it is 4. So the product terms or the value of k is 4. So we have an PLA with 3 inputs, 4 product terms or 4 AND gates, 2 OR gates, and 2. Okay, so such a PLA is given here, and this PLA we have 3 inputs is already found here. So we have 3 Boolean, 3 variable Boolean functions. So we have 3 variables, input variables. We have 4 product terms. These are the product terms. Also number them as 1, 2, 3, and 4. So these are the product terms, AND gates for the product terms. And 4 product terms and 4 AND gates, also numbered them with 1, 2, 3, and 4. Similarly, we have 2 outputs or number of outputs as m. So we have 2 outputs and 2 sum terms. So this is the value of m, which is 2, and this is the value of k, which is 4. And the total complemented lengths are n cross k. So n is 3 and k is 4. So 3 into 4 is 12. So 12 are normal lengths and 12 are complement lengths. Similarly, we have the value of k is 4. So 4 cross 2, which is 8. So we have total 8 lengths here, which you can see here. And m is the number of outputs. So we have 2 outputs, and every output look like this, taken from the OR gate and then passed through the inverter and fuse. So this is the desired PLA to implement these 2 Boolean functions, but this PLA has not yet been programmed. So we have to program it by looking into this PLA table, and we have to break some fuses, some lengths, so that would be the programming. After the programming, for example, if we look at the product term 1, we have to connect product term 1 or AND gate 1 to B prime and C prime and disconnect all other connections. And similarly, we have to connect product term 1 with sum term 1 and sum term 2, because they play a role in the, because they are part of the, this product term is part of the function f1 and f2. So to do that, to do this programming, at the end we would get a PLA like this. So we just break all the lengths and keep only the desired length. For example, to this gate, the length from B prime is kept, the length from C prime is kept. To this AND gate, the length from A prime is kept, the length from C prime is kept, and so on for the other product terms as well. Similarly, for the sum terms, is the sum term 1 gets the input from product term 1, 2, and 3, but not from product term 4. So we just break the connection from product term 4 to the sum term 1. And similarly, for the sum term 2, the connection from all the product terms should be given, but the connection from product term 3, which is here, should be broken. So this connection is broken. And finally, here, F1 we see C. So C means we have to break the fuse about the inverter, and T means we have to keep the fuse. We have to keep the connection about the inverter for the function F2. So for the F1, we just break the connection. So the connection goes through the inverter. So as we have considered F1 prime while calculating or creating the set of product terms. So that F1 prime is converted back to F1 by taking the complement, and that requires that this connection should be broken. F2 is normal, so we just keep the connection. This fuse is kept so that the function F2 is not inverted. So here it is just a bypass connection. So this is programmed PLA to implement the 2 Boolean functions.